In the realm of high-precision measurements, quantum mechanics presents a fundamental challenge: quantum noise. But what exactly is quantum noise, and why does it matter? Imagine trying to measure something incredibly small, like the movement of a single atom or the gravitational waves produced by distant black holes. At these scales, quantum fluctuations, random variations in energy and position due to the uncertainty principle, can disturb measurements, introducing an unavoidable background fuzziness. Quantum noise arises from two main effects: shot noise and quantum backaction noise. Shot noise occurs because light and electric current come in discrete packets, photons and electrons, rather than continuous waves. This leads to random variations in detection signals, limiting the accuracy of laser interferometry used in experiments like LIGO, Laser Interferometer Gravitational Wave Observatory, to detect gravitational waves. For example, if you shine a weak laser beam onto a detector, the number of arriving photons fluctuates, creating a grainy effect that interferes with precision measurements. On the other hand, quantum backaction noise arises from the observer effect, the idea that measuring a system inherently disturbs it. In ultra-precise atomic clocks and quantum sensors, measuring the position of a particle changes its momentum unpredictably, making repeated measurements unstable. This effect is particularly significant in optomechanical systems, where lasers are used to measure minuscule vibrations, such as those in nanoresonators, or mirrors in gravitational wave detectors. Why is this important? Quantum noise sets a fundamental limit on technologies that require extreme precision, such as quantum computing, atomic clocks, medical imaging, MRIs, and navigation systems. For example, in quantum computing, unwanted quantum noise can introduce errors in calculations, requiring sophisticated error correction techniques. Similarly, in biophotonics, where quantum light is used for ultrasensitive imaging of biological tissues, noise reduction is crucial for achieving higher resolution and contrast. Can we overcome quantum noise? Researchers are developing quantum-enhanced measurement techniques, such as squeezed light states, where the uncertainty of one variable, like photon phase, is reduced at the expense of increasing uncertainty in another, like photon amplitude. This has already been applied in LIGO, allowing it to detect weaker gravitational waves by suppressing shot noise. Additionally, advances in entangled particles and quantum error correction could lead to breakthroughs in ultra-precise metrology. What does the future hold? As quantum technology advances, mastering quantum noise could unlock next-generation sensors, faster quantum computers, and more accurate scientific instruments. Whether in space exploration, medical diagnostics, or fundamental physics, reducing quantum noise is key to pushing the boundaries of what we can measure and understand about the universe. Quantum noise arises due to the fundamental uncertainty in quantum systems, imposing limits on how precisely certain physical properties can be measured. This noise originates from quantum fluctuations, random variations in energy levels, electromagnetic fields, and particle positions, resulting from Heisenberg's uncertainty principle. Unlike classical noise, which can be reduced through better instrumentation, quantum noise is intrinsic to nature and sets fundamental limits on measurement sensitivity. Precision measurement systems, such as atomic clocks and gravitational wave detectors, must contend with quantum noise to achieve ultra-high accuracy. Quantum noise impacts atomic clocks by introducing uncertainties in atomic state transitions, which affects their timekeeping precision at the nanosecond scale. Quantum noise is like static on a radio. No matter how well-tuned the receiver is, a fundamental level of background interference remains. Shot noise arises because photons, electrons, and other particles arrive at detectors in discrete, random intervals rather than in a continuous stream. This leads to statistical fluctuations in the number of detected particles over a given time, limiting measurement precision. Shot noise follows Poisson statistics, meaning its magnitude scales with the square root of the total number of detected particles. As a result, increasing signal intensity can reduce shot noise but never eliminate it entirely. This phenomenon is a key limitation in optical and electronic precision measurements, particularly in quantum optics and microscopy. In gravitational wave observatories like LIGO, shot noise affects the precision of laser interferometers by introducing introducing fluctuations in photon arrival times, impacting the detection of tiny space-time distortions. Shot noise is like raindrops hitting a surface. Sometimes a few land close together, sometimes far apart, creating a random pattern that is impossible to smooth out completely. According to Heisenberg's uncertainty principle, measuring one property of a quantum system, such as position, inevitably disturbs its complementary property, such as momentum. This effect, known as quantum backaction, places a fundamental limit on precision measurements. In optomechanical systems and atomic force microscopy, where minute forces and displacements are measured, quantum backaction can introduce additional fluctuations that obscure the true signal. Overcoming this limitation requires techniques such as quantum squeezing or backaction evasion protocols. In quantum force sensing, measuring the position of a tiny mechanical oscillator with a laser alters its momentum, introducing noise that affects future measurements. Quantum backaction is like trying to measure the temperature of a delicate system with a thermometer. The thermometer itself slightly alters the temperature being measured. The standard quantum limit equal represents the lowest noise level achievable in a measurement system without special quantum techniques. It arises due to the interplay between shot noise from discrete particles and quantum backaction from measurement-induced disturbances. This limit poses challenges for ultrasensitive experiments in quantum metrology, such as measuring weak magnetic fields, gravitational waves, or atomic interactions. Overcoming the sequel requires using non-classical quantum states, such as squeezed states of light, to reduce uncertainty in one observable while tolerating increased uncertainty in another. In high-precision interferometers, quantum squeezing techniques have been employed to push beyond the SQL, improving gravitational wave detection capabilities. The sequel is like the best achievable balance between two opposing forces, like balancing on a tightrope where shifting too much in one direction leads to instability. Squeezed states are special quantum states where noise is redistributed between conjugate variables such as phase and amplitude in light waves. By reducing uncertainty in one parameter while increasing it in another, squeezed states enable measurements that surpass the standard quantum limit. This technique is widely used in quantum optics and precision sensors, allowing for enhanced measurement sensitivity without violating fundamental quantum principles. LIGO and Virgo observatories use squeezed light to reduce phase noise in laser interferometry, enabling the detection of gravitational waves from distant black hole mergers. Squeezing quantum noise is like pinching a balloon. The total volume remains constant, but pressure is redistributed to make one dimension more predictable. Quantum decoherence occurs when a quantum system interacts with its environment, causing it to lose its delicate quantum properties and behave more classically. This transition introduces additional noise that limits precision measurements. In quantum computing and metrology, decoherence manifests as random phase shifts, loss of quantum coherence, and reduced signal fidelity. Overcoming decoherence requires isolating quantum systems from environmental interactions and employing error correction techniques. In superconducting quantum computers, decoherence due to thermal noise and electromagnetic fluctuations limits the coherence time of qubits, reducing computational accuracy. Decoherence is like a foggy mirror. Initially clear reflections become distorted over time due to external interference. Quantum entanglement allows multiple particles to share correlated quantum states, reducing measurement uncertainty beyond classical limits. By exploiting entangled photon pairs, or atomic ensembles, researchers can perform measurements with enhanced precision. This technique is fundamental in quantum-enhanced metrology, atomic clocks, and magnetometry, where correlated quantum states help reduce statistical noise and improve sensitivity. Entangled atomic clocks have demonstrated higher precision than independent clocks, reducing the uncertainty in timekeeping and frequency measurements. Entanglement is like synchronized dancers, moving in perfect coordination, reducing uncertainty in their collective motion. Superconducting circuits, such as Josephson junctions and quantum squid sensors, are extremely sensitive to quantum noise. At ultra-low temperatures, fluctuations in electron behavior and superconducting phase states introduce measurement errors. These effects limit the precision of quantum magnetometers, quantum processors, and nanoscale voltage detectors. Advanced cooling techniques and noise isolation strategies are required to mitigate these fluctuations. Quantum squid sensors are used to detect minute changes in magnetic fields, but must be operated at cryogenic temperatures to minimize quantum noise interference. Quantum noise in superconducting circuits is like a finely tuned violin string. Small fluctuations can disrupt the perfect resonance, affecting performance. Advancements in quantum technology are pushing the boundaries of precision measurement beyond classical limits. Emerging strategies include quantum feedback control, adaptive measurement schemes, and AI-assisted noise reduction. By integrating quantum entanglement, squeeze states, and novel detection methods, scientists aim to develop ultra-sensitive quantum sensors for applications in fundamental physics, medical imaging, and geophysics. As quantum engineering progresses, these techniques will enable groundbreaking discoveries and technological innovations. Quantum-enhanced magnetometers are being developed to detect neural activity in the brain with unprecedented resolution, opening new frontiers in neuroscience. Future quantum noise reduction techniques are like noise-canceling headphones, actively filtering out unwanted interference to enhance clarity and precision.